where the sun is shining, or?
It's my study, you know.
Or it's your lamps, I see. Okay.
Yeah, the lamps, exactly.
The famous study, as
Famous
pictured on
study.
number file, I think.
Yeah, right. Seen by millions. Yeah.
Anyway, today's experimental math seminar speaker is Colin Defant, who will talk about cumulants and stack sorting.
All right. So you can see my screen, I'm guessing, right?
Yes.
Yes.
Okay.
As usual, feel free to interrupt, unmute yourself and mute yourself back. Thank you.
Yeah. So yeah, I put the slides for the talk in the chat. So if you want, you can look at those. But basically, this talk is going to be about this preprint of mine called Troops, Cumulants, and Stack Sorting. And this is a paper that has three main parts. And the parts are not troops, cumulants, and stack sorting. They're troops and cumulants, cumulants and stack sorting, and stack sorting and troops. And I've already given virtual talks about troops and cumulants and stack sorting and troops. So now I'm sort of completing the trilogy and talking about cumulants and stack sorting. So I'm not going to be talking about troops, but I'll just say briefly what they are. These are sort of families of colored binary plane trees that provide a broad framework for generalizing many of the things that I'll talk about in this talk, and saying they also allow me to generalize some other things. So if you want, I can tell you about them after the talk, but here I'm just going to focus on cumulants and stack sorting. So a permutation of size n is an ordering of the numbers from 1 to n, and I'll let Sn be the set of permutations of size n. A descent of a permutation is just an index I, such that the ith entry of the permutation is bigger than the I plus first entry, and I'll let des of pi be the number of descents of pi. An inversion of pi is a pair of indices I comma j, such that I is less than j, and the ith entry of pi is bigger than the jth entry of pi. I'll let inv of pi be the number of inversions of pi. And so as an example, if I look at this permutation 3, 1, 4, 5, 2, this is a permutation of size 5. Its descents are 1 and 4. 1 is a descent because the first entry is bigger than the second. 4 is a descent because the fourth entry is bigger than the fifth. So the number of descents is 2. And if you want, you can count the number of inversions and find that it's 4. So the main object that I'm going to be studying here is called West's stack sorting map. And this is a function that I'll denote by S. It sends permutations of size n to permutations of size n. And usually when I give a talk about this, I define it in terms of a stack, which is how West originally defined it. But I thought I'd shake things up a bit here and give a recursive definition. So first, S is going to send the empty permutation to the empty permutation. And then if you have a non-empty permutation, you can write it as L in R, where n is the biggest number in the permutation. L is the stuff to the left of n, and R is the stuff to the right of n. And then you just define S of L in R to be S of L followed by S of R followed by n. So as an example, if I wanted to find S of 416352, then n here would be 6. So L is 41 and R is 352. So this is going to split up into S of 41, S of 352, 6. Then to figure out what S of 41 is, well, I actually have to define S on these sort of partial permutations like 41 and 352, but I'm doing the same procedure, so it's pretty much the same rule. Here, the biggest number is the 4. So L is empty in this case, and R is 1. So this should be S of empty, which is empty, followed by S of 1, which is S of 1, followed by 4. Similarly, S of 352 is going to be S of 3, followed by S of 2, followed by 5. And then there's still 6 at the end. And then S of 1 is 1, S of 3 is 3, and S of 2 is 2. So this ends up being 1, 4, 3, 2, 5, 6. So we started with some permutation. We get some new permutation. And I could talk for days about this function because it has tons of interesting properties. And I'm not going to talk for days about it here, but I will just say the reason it's called a sorting map is because if you take some permutation, like 4, 1, 6, 3, 5, 2, and you apply the stack sorting map to it, you get some new permutation. If you then apply the stack sorting map to that, you get another permutation. And if you keep doing this over and over again, eventually you'll get to the identity permutation, just the increasing permutation 1, 2, 3, 4, dot, 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 n. Okay? So that's why it's called a sorting map. It eventually sorts your permutation. And people have asked things like, how many permutations require at most 1 iteration of this map to get sorted? How many require at most 2 iterations to get sorted? Those were actually originally enumerated by Doron Zeilberger. I'm not going to be focusing on those questions in this talk. Instead, I'm going to be looking at these questions here. So the first question is, how big is the image of this function? So how many permutations can I obtain as the output of this stack sorting map? Another question is, if I choose some permutation of size n, and I apply the stack sorting map to it, and then I count the number of descents, how big can this be? And how small could this be? You might think maybe this should be somewhat smaller than the number of descents of sigma itself, because you can think of the stack sorting map as a sorting map. So maybe S of sigma should be somewhat closer to the identity permutation than sigma was. And you can think of the number of descents as being a measure of how far you are from the identity permutation. If you have a lot of descents, you're very far from the identity. If you have very few descents, then you're very close to the identity. And similarly, if we were to choose sigma uniformly at random from Sn, then we could ask, what is the expected value of the number of descents of S of sigma? Again, we might expect this should be somewhat smaller than the expected value of the number of descents of sigma itself, which would be about n over 2. And finally, Julian West defined the fertility of a permutation pi to be the number of pre-images of pi under this stack sorting map. So the last question here is, how can we efficiently compute fertilities of permutations? If you give me some permutation, how can I efficiently figure out how many pre-images it has under this map? So here are some answers to these questions, not all of them. But first, Bousquet-Milou found a recurrence for computing the size of the image of this function. And you can use this to compute the first, say, 1,000 values of this sequence. So that's not hard to do with a computer. But the asymptotics of the sequence are still not very well understood. So even though we can compute 1,000 values of the sequence, we still don't really understand the long-term behavior in terms of asymptotics. Now, I proved that if you take this limit here, where I'm looking at the proportion of permutations of size n that lie in the image of the stack sorting map, and then I'm taking the nth root of that, this limit exists, and it's at least 0.68631. So the way I prove this is by using a variant of Fichte's lemma, which is due to De Broglie and Erdős. And then I get the lower bound by basically using Bousquet-Milou's recurrence to compute about 1,000 values of this series. So I'm not really doing anything terribly sophisticated here. I mean, there is an idea involved, but it's not terribly sophisticated, at least compared to what I'll say later about the upper bound. So later I'll give you an upper bound for this, and that's going to require a lot of the tools and the machinery that I'll develop throughout the talk. Okay. The next question was looking at these descents after we apply the stack sorting map to some permutation of size n. And it turns out this is somewhere between 0 and n minus 1 over 2. And these bounds are both tight. I actually like the upper bound a lot because when I was an undergraduate at the University of Florida, that was when I first did my first work on stack sorting. And I took a course with Miklos Bona on the combinatorics of permutations. And he had an exam in his class. And his exams are really hard because each one has only 3 questions. So if you miss one question, you're already down to a 67%. And each question requires some kind of an idea or an insight or something. I remember I flipped open to the second question on one of the exams, and it said, find the maximum number of descents that a permutation in the image of the stack sorting map can have. In other words, figure out what this upper bound should be. And I remember I stared at it for a couple seconds, and then I raised my hand and I said, am I allowed to cite my own theorem? And he said, oh, yeah, sure. And so then I was able to actually solve the exam question by citing my own theorem, which I thought was really cool. I still think it was pretty cool, but anyway, that's why I like the upper bound. The lower bound actually goes back to the work of Knuth from
Because I don't understand. Miklos Bona gave a problem in a test that is something that you wrote in a paper?
Sort of. I could prove it by using my theorem, but you didn't need my theorem to do it. My theorem was kind of an overkill.
So it was a difficult question, but it was still fair.
Yeah, it was still fair, and it was very easy if you happen to know my theorem,
Okay.
which I happen to know my theorem. Yeah. So Knuth actually showed that, and this was before West, but he defined sort of a precursor of West's stack sorting map. He showed that the number of descents of S of sigma is 0. Of course, this is the same as saying that S of sigma is the identity permutation. If and only if sigma avoids the pattern 2, 3, 1. And he showed that the number of such permutations is the nth Catalan number. And throughout this talk, I'll let capital C's denote Catalan numbers. This is just 1 over n plus 1, 2 n choose n. And this theorem is really important, not only because it was sort of the first start of stack sorting, but also because it was the first impetus for people to study permutation patterns, which is now a huge area of research. And also because it was the first time that someone used what's now called the kernel method, which is a really useful tool in analytic combinatorics. So Michael Engen, Jordan Miller, and I looked at this upper bound, and we showed that it is attained. In other words, the number of descent of S of sigma is equal to n-1/2, if and only if S of sigma is uniquely sorted. Uniquely sorted just means that it has exactly one preimage under the stack sorting map. And of course, that preimage must be sigma itself. And I'll just say here that these uniquely sorted permutations have a lot of interesting properties. I've written a couple papers about them, and then Hannah Malarchik now has a really nice paper about them, and also Mihir Singhal has a paper looking at them. So they have a bunch of really interesting properties. I'm going to talk a little about them at the end of the talk, but I won't say so much about them. Okay, and then finally, I had this question about computing fertilities of permutations. And in order to answer that question, I need to fix some notation involving set partitions. So let's say I have some sequence of numbers U sub n. So just think of this as some sequence of, say, complex numbers. It really could be any sequence of elements of a ring, but just think of it as a sequence of complex numbers. And I have a set partition rho. And throughout this talk, when I say a set partition, I mean it's a partition of the set of integers from 1 to n. So it's just some collection of non-empty disjoint subsets of the numbers from 1 to n, whose union is the entire set of integers from 1 to n. Then if I write U sub dot sub rho, this just means take the sizes of the blocks of rho. So the sets in a set partition are called the blocks. Take the sizes of the blocks of rho and plug them in for the dot, and then just take the product of this. So as an example, if I let, again, C sub m be the nth Catalan number, and I let rho be this set partition here, which has a block of size 4, a block of size 1, a block of size 3, and another block of size 1, then if I were to write C sub dot minus 1 sub rho, this just means take the sizes of the blocks of rho, which are 4, 1, 3, and 1, and plug them in for this dot, and then multiply them all together. And if you do that in this case, you get 10. Okay, so hopefully this is pretty clear. Now, in order to compute fertilities of permutations, I have to define these objects that I call valid hook configurations. And to start, I'm going to take the permutation whose fertility I want to compute, and I'm going to plot it. This just means I draw a bunch of points where the heights of the points correspond to the numbers in the permutation, and I read the heights from left to right to get my permutation. So for example, this would correspond to the permutation 7, 11, 10, 13, 3, 2, 6, 8, 1, 4, 5, 9, 12, 14, 15. So it's the plot of some permutation. And a descent top of the plot of a permutation is just a point that is higher up than the thing immediately to its right. For example, the descent tops here are the 11 because it's higher up than the 10, the 13 because it's higher up than the 3 because it's higher than the 2, and the 8 because it's higher than the 1. So the descent tops here are the 11, the 13, the 3, and the 8. And now I'm going to draw what I call hooks on this diagram. A hook is where I start at one of these points, I move vertically upward, and then I move horizontally to the right to connect with another one of these points. So this gives me some configuration of hooks. And I'm going to say that this configuration of hooks is a valid hook configuration if it satisfies 3 special properties. So here are the special properties. First of all, the southwest endpoints of the hooks have to be the same as the descent tops of the plot of the permutation. So see, every hook has a southwest endpoint, and you can see the southwest endpoints here are the 11, the 13, the 3, and the 8, which are exactly the descent tops of this permutation. So that's rule number 1. And notice that this implies that the number of hooks I draw has to be the same as the number of descents of the permutation, right? So this was some permutation with 4 descents, and that's why I had to draw 4 hooks. The second rule just says that a hook is not allowed to pass underneath one of the points in the plot. So for example, I would not be allowed to connect the 11 with the 12 using some hook, because that hook would have to pass underneath the 13, and that would be bad. So hooks cannot pass underneath points. That's rule number 2. And finally, rule number 3 says that the hooks cannot cross each other and they can't overlap with each other. They can kind of touch each other, like these two here, where the southwest endpoint of one is the same as the northeast endpoint of the other. So they're kind of kissing like this. But other than that, 2 hooks can't cross each other and they cannot overlap. So you can see that this is a valid hook configuration because it satisfies those 3 properties. Now this is going to induce a coloring of this diagram. The way we color the diagram is we start by drawing a sky over the entire diagram, and we color the sky blue, obviously, because the sky is blue. And then we color all of the hooks with arbitrary, distinct, non-blue colors. So this just means color all of the hooks with different colors, and it doesn't matter what colors you use as long as you don't use blue, because we already use blue for the sky. Now, this will induce a coloring of all of these points. The way I color a point is I just tell that point to look upward. And whatever color it sees, when it looks up, it becomes that color. For example, the 12 looks up and sees the green hook, so it becomes green. The 7 looks up and sees the sky, so it becomes blue. Now, there are a couple of caveats here. One is that the southwest endpoint of a hook doesn't see that hook. So for example, the 11 doesn't see the red hook, which is why it's blue, because it sees the sky instead. Similarly, that's why the 3 and the 8 are green instead of purple and orange. And the other caveat is that the northeast endpoint of a hook always gets the same color as that hook. So that's why the 13 is red, the 15 is green, the 9 is orange, and the 6 is purple. Okay, so I know this is sort of a lot, but just think of it as it's some coloring, and it's induced by the valid hook configuration. So I just chose.
Can I ask something? The hooks
Yeah,
are
sure.
now unique. There's a unique way for the hooks to be drawn now, I assume.
So the hooks I could have, I mean, when I chose the hooks like this, there were other choices. I could have, for example, connected the 8 up to the 12 instead of the 9. That would give me another valid hook configuration of the same permutation.
Uh-huh.
It is true, though, that once I have the hooks chosen, like I have here, this determines the coloring up to, of course, the specific colors that I choose. Like I could have chosen something else instead of red, but obviously that doesn't matter. Other than that, the coloring is induced by the valid hook configuration.
Okay, good.
Okay.
Yeah, thank you.
So now I'm going to take all of these 15 points and the sky, and
Is
I'm
it
going
obvious it always exists?
No, and it doesn't always exist, and that'll actually show up a little later. So in fact, a valid hook configuration will exist if and only if the permutation is in the image of the stack sorting map. And I'll mention that a little bit later. So if I have one and I have this coloring, then I'm going to take all of these 15 points and the sky, and I'll slam them against a wall lying over on the left-hand side over here. And I get this set partition, basically by just saying that 2 numbers are in the same block of the partition if the points with those heights have the same color. So for example, one of the blocks in this partition would be 3, 8, 12, 14, 15, because those are the heights of the green points. Another one of the blocks would be 7, 11, and 16, because those are the heights of the blue points, where I'm thinking of the sky as a blue point with height 16. So the sky is actually important here. It's not just for decoration. Now, okay, I realize this is sort of a lot of definitions, but the last piece of terminology here is that I'm letting VHC of pi be the set of all valid hook configurations of the permutation pi. So again, as I just said, a permutation could have multiple valid hook configurations, and I'm letting VHC of pi be the set of all of them. It could have no valid hook configurations, in which case this is the empty set. And so then I'll let P of H, if H is a valid hook configuration, I let P of H be this set partition that I get by doing the coloring and slamming it against the wall over here. And notice that the number of blocks of this partition is 1 more than the number of descents of the permutation. This is just because the number of blocks is the same as the number of colors I'm using. And I get 1 color for every hook, plus 1 additional color blue for the sky. And so the number of blocks should be 1 more than the number of hooks. But remember, I said the number of hooks is the same as the number of descents of the permutation. That's why we have this. So the reason I've done all this is that I now have this fertility formula, which says that if I want to compute the fertility of an arbitrary permutation under the stack sorting map, the number of pre-images it has, then I just sum over all of the valid hook configurations of that permutation. And for every valid hook configuration, I do this coloring and I slam the points against the wall to get the set partition P of H. I plug in the sizes of the blocks of P of H for this dot, and I take the product where the C's here are Catalan numbers. So this is just a sum of products of Catalan numbers where the sum is ranging over these valid hook configurations. And this ends up, so by the way, this is the theorem that I used in order to solve Bona's exam question, but you can solve the exam question without using this, this formula. So anyway, this formula is really useful for understanding a lot of properties.
So this is all stuff. Well, when you were an undergrad.
Yes, so this formula I proved as an undergrad. Later, I'll get into new stuff.
Okay.
Yeah. So it's really useful for doing a lot of different things about the stack sorting map, and also, solving exam questions in one case. But I want to convince you that even if you don't care about the stack sorting map, and I think you should because I think it's really interesting, but even if you don't care about it, I want to convince you that these valid hook configurations are actually really interesting. Because not only do they show up in this formula in a very natural way, but they also show up in a completely different context, which is the context of free probability theory. So free probability theory is an area of math that is fairly recent. It was introduced in the 1980s by Dan Voiculescu, and he used it to solve some long-standing open problems in the theory of operator algebras. And since then, it's found applications in random matrix theory and wireless communications and the representation theory of symmetric groups and a ton of different things. So it's this rapidly growing, very interesting area. I'm hardly going to tell you anything about it because it's a whole area of math. So I'm just going to give you the bare bones combinatorial aspects of what I'm going to need from free probability theory. So the first thing I'm going to do is I'm going to take some sequence of numbers. This could really just be any sequence of numbers, or really this could be any sequence of elements of any ring. But just think of it as a sequence of numbers, and I'm going to call it the moment sequence. So I call the numbers moments, but really it's just any sequence of numbers, and I'm just calling them moments. Then associated to this sequence is another sequence of numbers called the sequence of classical cumulants. And these two sequences are related by this formula, which says that the nth moment is given as a sum of products of classical cumulants, where the sum is ranging over all of the set partitions of the numbers from 1 to n. Okay, so for every set partition row, I take the sizes of the blocks of row, plug them in for this dot, and take the product. This gives me a sum of products of classical cumulants. So certainly this tells you that the moments are determined by the classical cumulants. But in fact, the classical cumulants are also determined by the moments. There's a way of inverting this by using Möbius inversion in order to express the classical cumulants in terms of the moments. Now, in free probability theory, people are interested in another sequence of numbers, which is called the sequence of free cumulants. And these are related to the moments via a similar formula, which says that, again, the nth moment is a sum of products of now free cumulants, but now the sum is ranging over non-crossing partitions of the numbers from 1 to n. So what is a non-crossing partition? Well, if I have a partition, I can draw its arch diagram where I basically connect numbers that are in the same block with these arches. And a partition is crossing if some of the arches from different blocks cross each other. And it's non-crossing if I can draw it so that none of the arches cross each other. So this is an example of a crossing partition. This is a non-crossing partition. And non-crossing partitions are really cool. They have a lot of interesting properties, and they show up in a lot of places, including free probability theory. And again, this is saying that the nth moment is determined by the free cumulants, but also you can invert this in order to express the free cumulants in terms of the moment. So what I'm saying here is any one of these three sequences will determine the other two. So that means that if you give me some sequence of, say, free cumulants, you say, okay, here's a sequence of numbers. These are the free cumulants. Figure out what the corresponding classical cumulants are. I would say, okay, sure. I'll just use the bottom formula to figure out what the moments are. And then I'll invert the top formula in order to figure out what the classical cumulants are. But when you do this, it's a little weird because you get this double sum and there's like a Möbius function flying around, and it's not really clear from a combinatorial point of view what's actually going on. Another approach you could try to take is to use generating functions. Because one of the powerful things about free probability theory is that it gives us methods for manipulating the generating functions for these sequences. However, if you try to convert from the generating function for free cumulants to the generating function for classical cumulants, what you end up doing is taking a compositional inverse and then dividing by 1 plus x, then taking another compositional inverse, then taking an inverse Laplace transform, then adding 1 and taking a logarithm. So it's this terrible nightmarish procedure with inverse Laplace transforms and logarithms, and it's just kind of a mess. So ideally, we like to have some nice combinatorial description of what's really going on when we convert from a sequence of free cumulants to the corresponding classical cumulants. And it turns out that we can actually do this using these valid hook configurations. So this is what I call the VHC cumulant formula. So VHC here stands for valid hook configuration. And so this says that if you give me some sequence of free cumulants, then the corresponding classical cumulants can be obtained by this formula, which is just given by summing over all of the valid hook configurations of all permutations of size n minus 1. So this here is the set of all of the valid hook configurations of all of the permutations of size n minus 1. For every one of them, I take this set partition by doing the coloring and slamming it against the wall. I plug in the sizes of the blocks of this partition for the dot, take the product. So this is a sum of products of free cumulants, and it ends up being these classical cumulants. Okay. So I think this is kind of just miraculous that this works, because I invented these valid hook configurations in order to understand stack sorting. And for a long time, I was just using them to understand stack sorting. And then it turns out that they show up in this very natural canonical way in this formula in free probability theory, which I think is just very strange that this happens to work. And it's really useful because since this is given as a sum over valid hook configurations, and so is the fertility formula, we're going to be able to combine those two formulas and use tools from free probability theory in order to understand things about the stack sorting map. So that's what I'm going to be doing throughout the rest of the talk. Okay. So the first thing,
Colin, this is very elegant, but
yeah, thank you.
computationally it looks very heavy if you use it to compute things. Do I have exponential size sets here?
Right. So there should be more than exponential size valid hook configurations. I know asymptotically how many there are, which is actually what I'm about to say. However, there are some tricks you can do, I think, by you can decompose valid hook configurations in a nice way, and so that can help with some things. I'll mention some of this a little bit later, but the nice thing about this is sort of for proving things by combining it with the fertility formula. So I want to count these valid hook configurations. And I can do that by setting my free cumulants to all be -1, right? So the power here is that I have the freedom to choose my free cumulants to be anything I want them to be. So I'm just going to set them all equal to -1. And if I do that, all of these negative kappas are just going to be 1. So then this is just a product of 1s. So I get a sum of a bunch of 1s. So I'm just counting these valid hook configurations of permutations of size n minus 1. So that's what I'm saying here. If kappa sub n is -1 for every n, then the formula for the number of valid hook configurations of permutations of size n minus 1 is just the negative of the corresponding classical cumulant. And I can use this to get a very explicit formula for the exponential generating function that's counting these valid hook configurations. And so it's this negative logarithm of 1 minus z times this generalized hypergeometric function thing. If you don't know what this means, it's not really important for the rest of the talk. Just know that it's some very explicit thing. So it's some very explicit thing that we can write down, and it's counting these valid hook configurations. Now, the way I'm getting this is by using these generating function tools that I mentioned before. Remember, I said you do this inverse Laplace transform, and there's a logarithm and compositional inverses, and I said it's this nightmarish procedure. Well, it turns out that when the sequence of free cumulants is this nice, it's just a bunch of -1s, I can actually handle it in this case. And so that allows me to get this explicit formula that's counting these valid hook configurations. Now you might think, well, who cares? You know, there's just some objects that you came up with. Why do you care how many of them there are? Well, first of all, I think it's interesting that we can count them because they're not easy to count. And that should be pretty apparent from the answer we're getting, right? The fact that this is not just Catalan numbers or Motzkin numbers or powers of 2 or something. This is some kind of weird, complicated thing, but it's still very explicit. And so this is saying that we're actually using free probability theory to count things that are difficult to count. That I think is sort of interesting in its own right.
So you get a sequence here. Is this in the OAIS?
I believe I've entered into the OAIS. Yes.
Great.
Yeah. Now, another reason this is nice is because I can actually use this to say something about the stack sorting map. And this goes back to the first thing I mentioned about this limit, which is measuring the size of the image of the stack sorting map. So remember, I said that I have this limit and it exists, and now I can give you this upper bound. So how do I get the upper bound? Well, remember, let's go back to the fertility formula for a second. This goes back to the question of whether these valid hook configurations exist. They don't always exist for any permutation. What this formula tells me is that if a permutation pi does not have any valid hook configurations, then it can't be in the image of the stack sorting map. And in fact, that's if and only if. So the contrapositive of this is saying that if you have a permutation in the image of the stack sorting map, it must have a valid hook configuration. And so the total number of permutations in the image must be at most the number of valid hook configurations. And so I sort of get this upper bound for free by just getting an asymptotic formula for these valid hook configurations. And I can get an exact, explicit asymptotic formula that's counting these valid hook configurations by just doing some singularity analysis with this generating function that I've written down here. So I basically get this upper bound for free from this previous theorem if I combine it with the fertility formula. Okay.
And
Okay,
this
so
is the best you can do. It's still a pretty large
Yeah,
gap.
So it's still a gap, and I would be very happy if someone could improve this. But yeah, so far this is the best I know how to do. Yeah. Okay, but now I want to tell you about my favorite application of this method, which goes back to this question of descents. So remember, if we take a permutation of size n, we apply the stack sorting map to it, and we count the number of descents in that permutation. This will be somewhere between 0 and n-1/2. So let's say that I choose my permutation sigma uniformly at random, and I want to know the expected value of the number of descents. I remember I thought of this question when I was on a train going from New York to Princeton. And when I was on the train, I thought, there's absolutely no way that this is going to have any nice answer. This is going to be some terrible mess. And I thought, well, okay, intuitively, this should be linear in the sense that if I take the expected value of the number of descents and I divide it by n, and then I let n go to infinity, then this should converge to some limit. But I thought, I don't even know how to show that that limit exists. And in fact, I still don't know how to show that that limit exists in any elementary way. But I can prove that it exists using these cumulants and the free probability. And not only does it exist, but it's actually very nice. It's just 3 minus e, where e is Euler's number. So it's just this very simple thing. And not only does the limit exist, but I can give you an exact formula for the expected value of the number of descents. I'm sort of shifting the indices a little here just to make the formula look a little nicer. So I'm taking a random permutation of size n-1, and I'm looking at the expected value of the number of descents plus 1, but that doesn't really make any difference. And I get this very simple formula. It's just 3 minus the truncation of the sum defining e times n. So it's sort of a shockingly simple formula, much simpler than anything I would have ever expected. And I'm getting this by using the cumulants and this combination of the VHC cumulant formula with the fertility formula. I can also tell you about the variance. I could write down an explicit formula, but it's kind of complicated, so I just gave you the asymptotics here. The variance is asymptotically 2 plus 2e minus e squared times n. And I can also algorithmically compute the higher central moments of this random variable here. And I computed the first 6 of them. And from the first 6, I conjectured that if you normalize it in this way by subtracting the mean and dividing by root n, then this should be asymptotically normally distributed. So I don't know how to prove this, but I can algorithmically compute these moments, and it seems to suggest that this is true.
Can I ask you something, Colin? The
Sure.
sum there comes up in when you're studying derangements. Is that an accident, or is that obvious? The harmonic number you've got inside
Right.
the parenthesis.
So I don't know how it's related. I don't have an obvious reason why it would be related to that.
Okay.
Yeah, it kind of just falls out magically from the proof that I give, and I still don't understand why it's this nice.
But you
It's-
might
it's
look
just-
for a simple combinatorial connection there. Yeah.
Right. I'll mention a possible approach that I haven't gotten to work in a minute. That would be like a simple combinatorial approach. But for now, let me just mention that the way I'm getting a hold of this expected value and the variance and these other moments is it's actually a consequence of this more general theorem here. And so this theorem says, first, I'm going to let f sub x of z be this weird thing here. Don't worry about what this is. It's just some expression involving x's and z's. So it's just something. What I care about here is these polynomials. So in this polynomial, I'm summing over all of the permutations of size n-1. And for each one of them, I'm letting the power of x keep track of the number of descents of s of sigma plus 1. So if I could understand these polynomials, that would tell me everything I wanted to know from the previous slide. It would tell me about the expected number of descents, the variance, all of that. It would follow if I could understand this. So I take the exponential generating function for these polynomials with respect to the variable z, and it ends up being this expression here. This is the negative logarithm of 1 plus the inverse Laplace transform with respect to t of f sub x of 1 over t of z. Okay, so don't worry about what this is. It's just some kind of weird thing, but it's pretty explicit. At least it's explicit enough for me to get the things that I had from the previous slide, like the expected value. It's following from this expression. This is kind of a pain to work with because of the inverse Laplace transform, but for the most part, it's explicit enough to prove things like the formula for the expected value. And so now the question is, well, how do I get this? And this is using the cumulants and the free probability. So I'm going to choose my sequence of free cumulants by letting kappa sub n be negative x times the n minus first Catalan number. So here x is just some variable. So I'm choosing my free cumulants to be this. Then I combine the VHC cumulant formula with the fertility formula and this observation from before that the number of blocks in a set partition associated to a valid hook configuration is the number of descents of the permutation plus 1. So remember, I mentioned this earlier, and this is where it's showing up. So I'm combining all of these things, and this ends up implying that the classical cumulants that I get, these little c sub n's, are precisely these polynomials that I care about over here. But then I can figure out what the exponential generating function for them is using this terrible nightmarish procedure that I mentioned before with the inverse Laplace transform and the logarithm and all that. That's, of course, why I'm getting inverse Laplace transform and logarithm showing up here. It's because I'm using those tools. So what I like about this is I'm sort of combining all of these different things that I've mentioned so far in this talk, and they're being combined in this right way to get this corollary just about expected value of the number of descents. So I'm combining the VHC cumulant formula, the fertility formula, this observation about the number of descents, this generating function stuff that I mentioned with the logarithm and the inverse Laplace transform. And it's all coming together in the right way to prove this fact about the expected value of the number of descents after you apply the stack sorting map is asymptotically 3 minus e. So that's why I like this. I like the formula that I had. So this explicit formula, I think it's a nice, cute formula, and it's much simpler than what I would have thought it would be. But the real reason I like this is because it's using all of these tools in the right way. Okay. I'll just mention that I've conjectured that these polynomials are real rooted. This would imply that they are log concave and that therefore the coefficients are unimodal. I don't know how hard this is to prove. I expect the real rootedness could be hard. I'm not sure about the unimodality. And I've checked this for n up to 33. So let me just mention that there's no way I would have checked this far by brute force if I was just looking at all permutations of size 32. There are too many of them. I was actually using this formula here in order to make this check to verify that this is true this far. Okay. So now let me tell you about some weird stuff. So let's say we try to give an elementary combinatorial proof of this fact that the expected value of the number of descents is asymptotically 3 minus e times n. One way you could try to do this would be to just ask, what is the probability that the number 1 is a descent of S of sigma? So you choose your random permutation sigma, apply the stack sorting map, ask, what is the probability that the first number in S of sigma is bigger than the second number? And try to show that that is asymptotically 3 minus e. And then try to do the same thing with 2. Try to show that the probability that 2 is a descent is asymptotically 3 minus e, and do the same thing with 3 and 4 and 5. And maybe if you could do this, you could show that the total number of descents is asymptotically 3 minus e times n. And this actually kind of starts to work. It turns out that if you choose your permutation sigma uniformly at random from Sn minus 1, then the probability that 1 is a descent of S of sigma is asymptotically 3 minus e. And I can prove this in an elementary way. So there's no cumulants or free probability or anything showing up here. It's just sort of an intricate combinatorial argument. But what's weird is that this doesn't work when 1 is replaced by 2. It appears that the probability that 2 is a descent of S of sigma is not asymptotically 3 minus e. It's some other thing. So I'm getting 3 minus e in 2 different situations. And my question is, why is this happening? So this is sort of my open question here. Why am I getting the same number in both of these cases? I do one computation using free probability and I get 3 minus e. I do a completely different combinatorial argument and I get 3 minus e in the other case. So why am I getting the same exact number? I have no idea. So this is my open question. So I do believe there should be some other explanation underlying this, but for
And
now I
do you
don't
have
really
an
know what it is.
Do you have an explicit expression for 2 and other cases?
No, I don't. I think I guess I didn't actually prove that it's not 3 minus E, but I think experimentally, okay, so it's an experimental math talk. Experimentally, it appears to not be 3 minus E. Okay, so yeah. I guess yeah. So I'll just leave it at that. A little more weird stuff comes from saying, okay, let's think of the number of descents of my permutation as a measure of how far it is from the identity permutation. I could also use the number of inversions, or I could look at the number of what are called inverse descents. These are just the descents of the inverse permutation. And I can actually write down explicitly what the expected values of these things are. So here H sub r is the harmonic sum, and so these harmonic sums are showing up here. And I can write these down explicitly, and this doesn't use cumulants or free probability. I can give a simple combinatorial proof of these expressions here, and I have these asymptotic forms here. So this isn't trivial, but it's not using cumulants or free probability. But what's weird about this is that this is saying, if you go back to the 3 minus E result, that's saying if you take a random permutation sigma, then you would expect sigma to have about n/2 descents on average. And then after you apply the stack sorting map, it has about 3 minus E times n descents. So the number of descents has decreased by about 43.7% if you work it out. However, these are saying that you're decreasing the number of inversions by about 0%, and you're decreasing the number of inverse descents by about 0%. So this is just because the expected number of inversions of sigma itself would be 1/2 n choose 2, and then I'm subtracting this lower order term in log n. And similarly, the expected number of inverse descents of sigma is n-1/2, and I'm subtracting this lower order term log n. So this is saying that if I'm thinking of how far my permutation is from the identity by looking at descents, the stack sorting map is doing a pretty good job of sorting the permutation. But if I'm using inversions or inverse descents, then it's doing a terrible job, which I think this is just strange that this different qualitative behavior shows up. Okay, so now for the last part of the talk, I just want to mention a couple other applications of this cumulants method here. So first, remember Michael Engen and Jordan Miller and I defined a permutation to be uniquely sorted if it has fertility 1, meaning it has exactly 1 preimage under the stack sorting map. And we show that these are the permutations that attain this maximum number of descents among permutations in the image of the stack sorting map. So how many of these things are there? How many uniquely sorted permutations are there of size n? Well, there's this sequence called Lassalle sequence. And it's given by this weird recurrence here. Don't worry about exactly what this is. It's just some weird recurrence involving Catalan numbers and binomial coefficients and stuff. And the reason this is called Lassalle sequence is because Lassalle proved that these numbers are positive and increasing. I don't know exactly what happened here, but Lassalle attributes this conjecture that these are positive and increasing to Doron-Zeilberger. Apparently in some private communication, Doron-Zeilberger conjectured maybe that these are positive and increasing. Lassalle proved this using symmetric functions and hypergeometric series. So the proof is completely algebraic, and it doesn't give any kind of a combinatorial interpretation for these numbers. In other words, we might think maybe they count something. And it turns out they do count something. They count these uniquely sorted permutations. So it turns out that the number of uniquely sorted permutations of size 2k plus 1 is the k plus first term in Lassalle sequence. And I should mention that I'm not looking at permutations of even size because there are no uniquely sorted permutations of even size. So I only care about the odd size. And I just get these Lassalle numbers.
But Lassalle has also counting something? The motivation of Lassalle?
No, I don't know at all what Lassalle's motivation was for studying this. But it turns out to be a really interesting sequence. Not only because they count these uniquely sorted permutations, but also because Novak observed that they are essentially the classical cumulants of something called the standard semicircular law. Okay, so basically what I'm saying here is that if you choose a sequence of free cumulants by letting kappa sub 2 be 1, and you let kappa sub n be 0 for all other n, then the corresponding classical cumulants are basically the Lassalle numbers, but with alternating signs. Okay. And I should mention that the proof that Michael Engen and Jordan Miller and I gave of this sort of predated the VHC cumulant formula in the way that I phrased it here, but now I've sort of gone back and figured out that the correct way to think about the proof is using this. And we just combine the VHC cumulant formula with the fertility formula, doing the same kind of stuff that I mentioned before, and we end up getting this very simple enumerative corollary. Maybe I should mention that the only way we were able to find that this was even a reasonable thing to try to prove was using the OEIS. So that was very helpful for this.
You're welcome.
Yeah. So the last thing I'll mention is the degree of non-invertibility. So this is a concept that Jim Propp and I introduced in a paper last year. So here we have some function f from a finite set x to itself. And we define the degree of non-invertibility of f to be this thing here, where we take 1 over the size of the set x times the sum of the squares of the number of pre-images of the various elements of x. Okay, and you can think of this as some kind of a measure of how far f is from being bijective. So it turns out that f will be a bijection if and only if this degree is 1. And then if the degree is big, you can think of f as being sort of far from being bijective. So we'd like to know, well, what is the degree of non-invertibility of the stack sorting map? We don't really know what it is. We know it grows exponentially, which is something. That's not really clear at all from the definition. But here we've taken the degree of non-invertibility to the power of 1 over n. We look at this limit. We've shown that it exists, which is not obvious either. And it's somewhere between 1.12 and 4. Now we have a conjecture. So this is sort of the other experimental math part of the experimental math talk. We have a conjecture that the degree of non-invertibility, this limit, is about 1.7. The only way we were able to make this conjecture was by using the fertility formula. Basically, we generated a bunch of random permutations of size 1000, and then we computed their fertilities by using the fertility formula. And then we did some averaging, and we end up, that's how we basically made this guess. But again, there's no way we could have made this conjecture to this degree of accuracy without having some kind of theory like the fertility formula. Now I've improved the lower bound that we had to about 1.62924. So remember the previous lower bound was 1.12. Now it's about 1.62, which is much closer to the 1.7. And I do this by using free probability. So here I'm choosing some sequence of free cumulants by letting kappa sub n be the negative of the n-1st Catalan number squared. Again, I choose I combine the VHC cumulant formula with the fertility formula in the right way. And I can use that to show that this limit that I care about is at least this supremum where these little c's are the classical cumulants. And then I just have to compute the value of this expression here for n equals, say, 1000. And that gives me my lower bound. So I should mention that I actually don't know how to figure out what these classical cumulants are explicitly. You might think, oh, just do the technique where you use the generating functions with the inverse Laplace transform and the logarithm and all that. It turns out that that's, I think, as far as I can tell, too complicated to do in this situation.
Can I make a quick suggestion?
Yes.
Have you tried using linear programming to optimize the choice of the free cumulants to maximize your lower bound?
No, I haven't. The reason I'm using them here is because the Catalan numbers show up in the fertility formula, and I'm squaring them because of basically the definition of the degree of non-invertibility involves squaring things. So sort of when you work it out and you do some inequalities, you find that I think the correct thing, at least as far as I could tell, the correct thing was to use squares of Catalan numbers. But maybe there is a different choice that would give something better. And I definitely haven't looked into that. So I just used this choice because it was sort of the natural choice based on how I want to combine the VHC cumulant formula and the fertility formula.
Sounds like a natural setup for linear programming.
Huh. Yeah, I can definitely think about that. So anyway, I guess that is everything that I wanted to say. So thank you everyone for coming. Usually when I give a talk about stack sorting, I define it with a stack and then these letters go in and out of a stack at the end. But here you can just imagine that you can recursively apply the stack sorting map to the letters and they're ordered in this way. And you get thanks. So thanks.
Thanks for a stimulating talk. Are there any questions?
Yes, I have a very quick question. when you were showing the formula for the generating function for counting these valid hook formulas, right?
Mhm.
So the generalized hypergeometric function showed up. So I'm suspecting that you were looking just at the series expansion and you identified these, but the generalized hypergeometric function also satisfies a very interesting ordinary differential equation. So what does that somehow mean? Did you look into that?
I definitely didn't look into that. Although the reason I got this was not actually experimentally. I basically just plugged in the -1 for the free cumulants and worked out what I ended up getting
Right.
just by going through the computations of the logarithm and the inverse Laplace transform, and it ended up being this.
Yeah.
But
But
yeah.
anyway, so this is, of course, an ODE that may show up in many contexts. And so now we know it counts something in this particular case where you choose the parameters as you do, right?
Right, and it's in the OEIS, so I would love it if someone could find some other objects that happen to be counted by these things, or maybe if there's some other, differential equation that people are looking at and maybe they come across the sequence. I think that would be really cool. I'm very hopeful that might
Can you
happen.
give a hint about how to locate it in the OEIS?
Oh, probably
like,
if you search
when?
search valid hook configurations, it would be there. Alternatively, if you go to my paper, Troops, Cumulants, and Stack Sorting, I do mention the OEIS number, I think, in there.
Okay.
Maybe. I
Well,
know
you
I mentioned
should.
several OEIS. Well, I mentioned several OEIS sequences there, and I can't remember if I mentioned this one.
Yeah.
But I think I do.
Yeah.
And
I
Colin,
know
I have
you're
a-
a regular contributor, so good.
I have a quick question. If you exponentiate both sides, it looks like exponential formula. So these are the connected components. And can you make it in combinatorial proof using exponential generating functions?
So you're sort of reverse engineering what I'm doing here. That is basically what is giving rise to the logarithms showing up here.
Mhm.
It's because basically this setup of converting from from classical cumulants to moments, this is just the exponential formula. And so that's why the logarithm is showing up here.
Any other questions? Well, let's thank Colin for a great talk. Thank you, Colin. Let's end this.
Yeah, thank you for having me.
Thank you.
Yeah, thanks a lot.
Thank you.
All right, thanks everyone for coming out. We'll see you back here again next week at the same time.
Thank you.
Thanks,
Have a
Rob.
good night.
Thank you.
Bye, everyone.
Bye.